Good afternoon to everyone. I'm Riccardo Porcedda from Università degli Studi di Milano-Bicocca, Italy. Today, my talk is going to be about the problem of explainability in the artificial intelligence field. The title of the paper, as you can see, is Interpretability is not explainability. So we will focus on the difference between these two concepts and the creation of a new taxonomy to better evaluate the explainability of AI models. First, we will start with a brief introduction and a problem statement. So now we live in a period of growing importance of artificial intelligence in various domains, including education, which is the field we tackle in this research. And there is the challenge of explainability in machine learning algorithms. There is a lack of consensus in literature on distinction between explainable and interpretable systems. There are some works, for example, the one from Gilpin et al., which focus on interpretability and completeness as key components of explainability. So here, explainability is viewed as a trade-off between interpretability and completeness. What are the challenges and the proposed solutions? First of all, we have to be cautious against an anthropocentric taxonomy due to potential biases. Nowadays, explainability of artificial intelligence models are evaluated not in a quantitative way, but in a qualitative way, using, for example, without surveys. But anyway, explainability requires a human in the loop process. Why is that? Because we are trying to evaluate how much a model is explainable to a human user. So in some way, we have to put the human inside the loop, but we have to be careful about that. So here we propose a taxonomic classification of all explainability-related concepts, and then we propose the construction of a pipeline to implement this framework in AI application. We will see two examples, one on a toy dataset, which is the well-known iris dataset, and then on the Merlot dataset, which is an education dataset used in our recommender system. So now we delve into the new taxonomy proposal, and here we unravel the notions of interpretability and explainability into more specific definitions, which are transparency, interpretability, explanation, completeness, complexity, understandability, and explainability. All of this to provide a formal mathematical framework for quantitative measures. First of all, we have transparency. Transparency is the cornerstone of explainability. It indicates how much fake is a model, and the opposite of transparency is, of course, black boxness. Here we have a formal definition. So a system is transparent if its inner mechanism is accessible, including the algorithm definition and the reconstruction of all operations executed by the algorithm itself. A system with maximum transparency is a white box, and with zero transparency is called a black box. This definition here that we gave actually encompasses the aspects of simulatability, the composibility, and algorithmic transparency, which are discussed in the work by Lipton, which you can find then later in the bibliography. What is a simulatability? A model is transparent if a person can contemplate the entire model at once, so suggesting that the model itself is simple and it allows humans to grasp its decision-making process. That's what simulatability is. Then we have the composibility, which means that not only we have a glance of the model, but also we have an intuitive explanation of how each part of the model works and which is his contribution to the decision-making process. And then finally we have the algorithmic transparency, which refers to the understandability of the training algorithm, allowing users to comprehend the rationale behind the model's development and behavior. From that, we go on with the interpretability. We already mentioned the work by Gilpin and Talia, and we base our framework on the definition of interpretability and completeness. So first of all, what is interpretability? A system is interpretable if it is possible to identify a relation between inputs and outputs. This relation can be a function, transformation, or a rule. A white box system has maximum interpretability and a black box has zero interpretability. And then, what is an explanation? An explanation is a reason or justification given for one or more outputs of a system. It can be in any form, but it must be intelligible. And what is the completeness of an explanation? The completeness actually measures its adherence to the interpretation. So we say that an explanation is complete if it actually describes the interpretation of the model that we have. And then we have the complexity. An explanation can be complex, more complex, less complex. So we have to measure the effort required by a user to understand it. How can we do that? For example, let's say that we have a model with a series of if-then classification rules, and we give these rules as explanation. We can propose a measure for their complexity, and it should satisfy these requirements. The effort to understand a classification rule increases with the number of if-then clauses. Rules with more than one if-then clause on the same feature are more complex, and a rule with only one if-then clause has the lowest complexity that we can put to 0. Here we propose this formula for the complexity of a rule. First of all, we have the length of the rule, which is actually the number of if-then clauses concatenated with an AND. Then we have K, which is the set of features used in the model. And then we have a subset of these features, which are the features actually used on the if-then clauses that we are analyzing. And then here we have finally a mathematical measure, quantitative measure of complexity. Then, after we have measured how complex a rule is, we have to say how much a complex rule is understood by user. Here we base the definition of understandability on the works of Guidotti, Pedreschi, Gianotti et alia, and also Arrieta et alia. First of all, in the first paper, Guidotti repeatedly emphasized how important it is to have an understandable explanation in order to obtain interpretable algorithms. And then, to address the definition, we refer to the work of Arrieta, which says that understandability denotes the characteristics of a model to make a human understand its function, so how the model works, without any need for explaining its internal structure or the algorithmic means by which the model processes data internally. What does this mean? It means that we want the user to understand the overall process decision making, but we don't want the user to actually understand all single steps that the algorithm does. So here we give a more simple definition which covers all that we said. So understandability of an explanation represents the user's capacity to reproduce the system's behavior as described by the explanation. This definition is the one that introduces the human-in-the-loop process, so subjectivity, as different users might have varying levels of understanding. And understandability should depend on two factors: the complexity of the explanation, for which we already gave a quantitative measure, and then the tolerable complexity for the user. And then we have a series of properties that we would like for this understandability function. First of all, we desire a function that has domain from 0 to infinity, so the complexity can go from 0 to infinity, and range from 0 to 1, which means that we would like an understandability measure which goes from 0 to 1. When the complexity is actually equal to the tolerable complexity, we would like this measure to have a value of 0.9. Of course, when the complexity of a rule is 0, we should have a complete understandability, so a value of 1. And when the complexity of the rule goes to infinity, it should go to 0. Additionally, we can desire a sigmoidal behavior to represent some ranges, which here we called of learning ease, saturation, and also learning decline. So for small values of this parameter, which is the rule complexity divided by the tolerable complexity, we would like a derivative of the understandability function which goes to 0, and also that for great values of that parameter, so the range of saturation. And then for intermediate values, we would like, as we said, for the sigmoidal behavior, a derivative which is between -1 and 0. And this is the range of learning decline. We propose two candidate functions which satisfy the conditions we already talked about. And these are the Gaussian decline and the squared hyperbolic tangent decline. We will see the difference between these two at the end in the results. Finally, we have our definition of explainability, which is different from interpretability, as we said. A system is explainable if it can provide the explanation of its inner mechanism, which are both complete and understandable. Operationally, we can say that the explainability of a system is the product of its interpretability, the completeness, and the understandability. Now, after we proposed a clear taxonomy of explainability-related concepts, we face a problem: how to improve the explainability of an artificial intelligence model. There is only one way to improve it when one explanation is not considered sufficient by the user, providing additional explanation. That's why we should have a measure of the total explainability for a given number of explanations with related explainability value. Here we have a list of the desired properties for the total explainability of two explanations with related values of explainability E1 and E2. First of all, we have the symmetry property. So the total explainability of E1 and E2 should be equal to the total explainability of E2 and E1. Then we would like the total explainability to be less or equal than 1, which is the maximum explainability, but also we would like, it would be reasonable to have a total explainability which has the maximum value more or which is greater or equal than the maximum value of the explainability of the two explanations provided. Then, of course, if we add an explanation with zero value explainability, it should add nothing to the explainability that we already have. So the total explainability of E1 and 0 should be equal to E1. Then we have the final property, which is the monotony property. If we have three explanations with the relative values E1, E2, and E3, which are in ascending order, then the total explainability of the explanation with values E1 and E2 should be less or equal than the total explainability of E2 and E3. We propose this function, and it is trivial to demonstrate that the first three properties are satisfied, but then attached to the paper, you found also the proof for the fourth property of monotony. So now we have the definition of a total explainability of two explanations. But then we could also provide more than two explanations. So we can have a recursive definition for a set of explanations. The idea is that for any value k, the total explainability can be computed on ek and a set of ek minus one explanations. Here you find a formal mathematical definition. And then we face the operational problem. We have the mathematical framework. What do we choose for augment the explainability of a model? We evaluated some methods, which are SHAP, Lime, and counterfactual, but then the chosen method was actually the SHAP package due to ease of implementation, computational efficiency, and also intuitive graphical explanation. SHAP is a package that uses Shapley values from game theory. What are Shapley values? Shapley values represent rewards in a collision game. Here, in the machine learning context, we can see the game as the classification task. The players should be the features of our model, and the payoff is actually the classification value. From these Shapley values, we can build an explanation model. How do we do that? First of all, we sample the collision vectors. We convert this vector to the original future space. We compute the weight of each collision vector using the SHAP kernel. And then we fit the explanation model and return the Shapley values. Then we have a list of metrics for the evaluation of the explainability with the SHAP obtained with the SHAP package. And we have a list of mask-based and resample-based metrics, which are proposed by Lumberg itself, which is the creator of the SHAP package. Mask-based metrics observe a model's output changes when features are masked. Resample-based metrics actually replace hidden features with random training sample values, and this metric does not make the assumption of model linearity, which could be quite useful when we deal with deep learning models which are nonlinear. Finally, we have the keep absolute resample, which measures the explanation method's ability to find most important features sorted by absolute Shapley value for model accuracy. Good explanation will enable the model to achieve high accuracy with only a few important features. In our classification task, we are interested in both positive and negative Shapley valued features. That's why we finally decided to use the keep absolute resample metric. And as a proxy for explainability, we can rely on the area under curve of the curve plotted. This allows us to quantitatively assess the quality of our explanations and make improvements where necessary. Here we show an example on a toy dataset, which is the well-known IRIS dataset. We use a support vector machine trained on this dataset using the scikit-learn package. And then we extract the rule of the support vector machine model using the SVM plus prototype algorithm, which you can find in the bibliography. Here you have an image to give you a hint of what this algorithm is about. First of all, we build the equation rules. This ellipse is actually build rules from the classification task, and then we build the hyperrectangles to build the interval for the rules. Here you can find all the precise steps. So we train the support vector machine, we identify the support vectors, we find the closest prototype for each support vector, and define the geometric shapes around the support vectors. And then we extract the rules. Here is the example using SHAP on the IRIS dataset, actually on the support vector machine model trained on the IRIS dataset. And we can see from this future importance plot built with Shapley values that petal length is the most important feature. Sepal width is the least important, and the contribution of these features, so sepal width, sepal length, and petal width, are close to 0. This feature importance plot can be viewed as an additional explanation given by using SHAP. And then here we also have the explainability of the support vector machine model, just evaluating the extracted rules. So here we are not evaluating the augmentation method. Here you can see the difference between the two candidate functions for understandability, and we can see that the total explainability obtained using the state function is slightly different for small values of this parameter, which is actually the complexity of the rules divided by the tolerable complexity. But then after we go further from the value of the complexity equal to the tolerable complexity, we can see that the two functions are virtually the same. And as desired, for a value of complexity equal to the tolerable complexity, we have an explanation value of 0.9. Then we apply the explainability augmentation method. We can see here the keep absolute resample metric, and after we evaluated the area under curve, we plug it in the new total explainability, and you can see that the shape is the same. Of course, it's the same function of how we evaluate explainability, but then when we were talking about only the super vector machine model, the explainability values started from 0. Now here we have explainability values of the model which start from nearly 0.7. So we actually augmented the explainability of the model. Now we go on with the implementation on our recommender system based on the Merlot dataset. Merlot dataset is a collection of educational resources and user ratings. So here you find example of the two data frames which are then joined. So the ratings and all the description of the resources using type, language, difficulty, format, duration, and the disciplines, of course. Here you can find the different discipline level. We merged the dataset, as we said, and then we also simulated the user preferences. Here we have an example of a user which looks for a resource with the discipline business, language English, and so on. Future correlation. This is a very important step because we are using kernel SHAP, and kernel SHAP does not perform very well when features are correlated. Why is that? Because kernel SHAP is not very capable of computing the conditional probabilities when features are correlated. So that's why we decided, as you can see here, you find that the discipline levels, as one could expect, are correlated, highly correlated, and that's why we decided to aggregate these features into one features to have lower correlation. Then we use the predict function of the kernel SHAP, and before that we had to do some one-hot encoding. Why is that? Because the SHAP package only wants numerical values, and our model also had text values. We use stratified sampling to obtain a background data set, which is needed for kernel SHAP. And then we have the results. Here we have the future importance plot built with Shapley values. Why we use this importance plot and why this is more desirable than other permutation-based methods? Because the importance with the Shapley values does not depend on the goodness of the model, but only on the magnitude of feature attributions. And here we can see that, as we could expect, the recommender system is mostly based on the discipline features and type feature, also difficulty, and which are the features we are looking the most when we look for an online resource. With just the first two most important features, a mask, the accuracy of the model reaches a value of 0.9. So we have a very good explainable model. The area under curve is 0.81, and we can use this value to augment the explainability of the model, the basic explainability of the model that we evaluated before using the SHAP package. So here we have the average model complexity, which is 4.06. Here we use the rule extraction method that we described above. And given the values of the area under curve, we can build the total explainability using both Gaussian and the squared hypertangent decline. And the new recommender system explainability value is in the range from 0.81 to 1, of course, depending on the value of the tolerable complexity of the user. Conclusions. We presented a new quantitative approach to explainable artificial intelligence. We introduced a formal taxonomy for this case study, and we emphasized that explainability is different from interpretability, which means that even white box models can benefit from explainable artificial intelligence research. Future work could include conducting studies in human-computer interaction to better understand how users manage complexity and consequently develop improved understandability functions. And then also considering user saturation by setting limits on the number of explanations provided. When we talked about the measure for a total explainability of the given explanation, we could reach the maximum explanation by giving lots of explanation in our framework. Of course, maybe a user, if too many explanations are provided, reaches as saturation limit, and then we cannot further improve our explainability. Thanks for your attention. You can find in the paper all the bibliography, and if you have any question, I will be happy to reply. Thanks.